Hi all of you. This is number system 2. I have posted one video on number system and that PPT had previous year CAT questions. So there was a demand, some students wanted one more session on number system and this was for the revision part. So this PPT has got around 5 slides with quite a few questions on one slide. But here the objective is not to cover the previous year CAT questions, but all the important aspects, those identities, theories, observations to be wrapped up and some or the other way in parallel cases or in corollary cases these identities might get used. So the objective is to cover those identities. So what all are the topics covered? LCM HCF, everybody knows LCM HCF, but we have seen in the past few years CAT use some questions where the conventional way of solving LCM HCF will not suffice. So just for that reason LCM and HCF topic is covered. Power cycle, this is again I told you the objective is to revise the things related to power cycle. Remainder theorem, um, most of the questions even last year or year before last year we saw remainder theorem questions coming. The first question I guess it was in year 2000. So for the last 25 years CAT has not stopped asking questions on that. But just to put some simplicity in it, we will have Euler's theorem to compare how the conventional modulus theorem is different from this and what is good and what is bad in it. Then factors related some theories, sum of all the integral factors and sum of all the odd factors, even factors, and then the other theory related to the addition, the identities of n natural numbers, identities of odd natural numbers, even natural numbers, addition of the first n perfect square, first n perfect cubes. Please understand, I'm not trying to say that we are expecting one question from this theory. No, there also can be a LR set in CAT where somehow, some or the other way, this will get used. You can have a DI question, some or the other way, this identity will be handy. And of course, some other chapters of maths that are coming ahead, this way or that way, when you are in middle way of the process of reaching the answer and somewhere you want to wrap up in a simple way, this can be handy. So these topics are more of a tools and don't expect questions directly. If it comes, we will be happier, but the objective is to sharpen the tools for almost all the sections. All right. So here's a question made just to solve it out and not just revise the theory as it is. So let's revise it through this question. The question is product of two natural numbers is given. That's 1, 4, 1, 1, 2. And their LCM is 1008, right? So the number of possible pair. So one identity you need to know is the product of LCM and HCF of two numbers is always equal to the product of two numbers. Say this is number 1 and this is number 2, right? So this is the first identity. We know the product is 14112 and we know the LCM is 1008. So by this we can find out the HCF first. So what is the HCF? 14112 divided by 1008. 14 sevens are 98, 14 twos are 28, 14 ones are 14, 14 eights are 112. Then what? 72 ones are 72, 288, 72 fours are 288. So the HCF is 14, right? We have got the HCF as 14, we have got the LCM. Now, how do we reach? We have to find out the total possible ways of getting N1 and N2 in different formats. So, N1 is the HCF which we have found out into some number. Let's say that number is A, and N2 is HCF which is 14 and some other number, let's say that is B. And remember, A and B should be relatively prime, because if they are not relatively prime, 14 will not act as the HCF, right? So the HCF of A and B should be 1. All right, so from this we can deduce LCM is the HCF into the co-prime numbers. And we know the HCF, LCM is how much? 1008. That is 14 into A into B. So we get A into B as 14 sevens are 98, 14 twos are 20. A into B is 72. And remember the statement A and B are co-prime numbers. So how can we have two co-prime numbers with the product as 72? So it can be 72 into 1 and it can be 8 into 9. 2 into 36, the HCF is 2. 3 into 24, the HCF is 3. 4 into 18, the HCF is 2. 5 will not go. 6 into 12 is 72, alright, but the HCF is 6. So the only option where the two numbers have HCF as 1 is 8 and 9, and obviously 72 and 1. So how many possible pairs are there? There are two possible pairs, 1 and 2. So that's the answer. The question has not asked what are the numbers, but if we were to answer that, we have got the possible values of A and B as 72 and 1 and 8 and 9. So the first, if I take this as 1, so 14 is 1 and this becomes 72. So 14 into 72, 14 sevens, 980 and 28, 1008. This is one pair. The other is, if A is 8, 14 eights are 112, then this is 9, 14 nines are 126. Question has not asked this, but in case question goes for that, what are the two pairs? It is this, and that's our answer. Actual answer is there are two possible pairs, right? So that's this question where it takes a revision of this identity. It makes you aware of how the non-conventional way of finding LCM is. It is this. LCM is HCF into this, right? What is the next question? Okay, this is just the way of getting that. That's basically for you to take the screenshot, but that was good enough for us. Second, what is the number in the units place of n, and n is a string of multiplication of such numbers. So these questions used to be very scary in the 2001, 2002 years, where CAT for the first time came up with this question. Now they are known to most of them. Even if the student is a fresher, this question comes in the textbooks and so many websites quite frequently. So it's not a surprise, it's just a revision for us. Number in the units place. So the power cycle of 1 is 1. We don't need to worry about that. Power cycle of 2 is 2. 2 into 2 is 4, 8 and 6. The power cycle of 3 is 3, 9, 7, 1. The power cycle of 4, 4 and 6. 4 raised to any odd number is 4. 4 raised to any even number ends with 6. That's it. Only two numbers in the power cycle of 4. 5 raised to anything ends with 5. 6 raised to anything ends with 6. Power cycle of 7. 7 raised to 1 is 7. 7 raised to 2 ends with 9. That's 49. 7 raised to 3 ends with 3. 7 cube is 343. 7 raised to 4 ends with 1. It's 2401. How about power cycle of 8? 8 raised to 1 is 8. 8 eights are 64. 8 cube is 512. And 2 into 8 ends with 16. How about 9? 9 raised to 1 is 9. 9 raised to 2 is 1. So 9 raised to any odd number ends with 9. 9 raised to any even number ends with 1. So that's the power cycle. Some questions also ask you the second last digit, right? There were a few occasions where CAT came up with not the last question, but CAT asked what is the second last digit. So that's also part of power cycle, but just understand that every number doesn't have a rhythm, a repetition in the second last digit. 7 does have. Right? You can also work similar way for second last digit in case of 7. Anyway, now let's focus on this question. The last digit of this is 1. The last digit of this is 122. There are 4 stops in a cycle of 2. So 122, forget about this. 2 raised to 120. 120 is a multiple of 4. 2 raised to 120 will surely end with the 4th stop. But it's 122. So 121, 122. So the second stop of the next cycle. So this will end with 4. Power cycle of this 3 is 3971. So every multiple of 4 that is there in the index will complete the cycle. So 3 raised to 123, forget about these digits. 120 is a multiple of 4. So 30 cycles will get completed. 120 divided by 4, 30 cycles will get completed. 31st cycle has got 3 stops. So first, second and third. So this will be 7. 4 raised to any even number ends with 6. 6 raised to anything ends with 6. Now this, we have again 4 stops in the cycle of 7. And this is 127. So 124 is a multiple of 4. So that will have 31 cycles. 124 divided by 4 is 31. 31 complete cycles, and 125, 126, 127. 3 stops in the new cycle. So third stop will be 1, 2 and 3. So this will end with 3. 128 raised to 128. Power cycle of 128 has got 4 stops. 128 incidentally is a multiple of 4. So it will end on the last stop. So the last digit of this will be 6. And 9 raised to any odd number ends with 9. So a final wrap up. 1 into 4 is 4. 4 into 7 ends with 8. 4 sevens are 28. 8 into 6 ends with 8. 8 into 6 is 48. It ends with 8. 8 threes are 24. It ends with 4. 4 6 are 24. It ends with 4. 4 nines are 36. And it ends with 6. Did I miss out on anything? I think it should be complete. 6 is the answer, and that's how the power cycle works. So I was just telling you there are cases where they came up with second last digit. So what you have to do in that case is it works for 7. I know, right? In case you don't know, you just have to try it out. How you have to try it out? 7 raised to 1 is 07. 7 raised to 2 is 49. 7 raised to 3, 7 cubed is 343. So the last 2 digits are this. 7 raised to 4 is square of 49. So half of 48 is 24, 2, 4 and 0, 1. You can simply multiply by 7. You don't need to know those Vedic maths and whatnot, whatnot. 7 threes are 21, 2 carry, 7 fours are 28 into 30, 0, 1. What is 7 raised to 5? This into 7. What is 7 raised to 6? It starts repeating. See? So now we have a cycle even for the second last digit. So it is 07, it is 49, it is 43, it is 01 and it goes on. So this can also be applied for second 9 digits. So I was telling you, can it be applied for any number? All the numbers don't have the same behavior. So the question doesn't get structured and then logic doesn't prevail. And that's why they focus only on the numbers where the repetition seems obvious. Okay. That's how the question was. Okay, what's the remainder when this is divided by 28? We discussed the Euler's theorem initially. So we can go, term by term, divide the left term by 28 and work out what is the remainder, divide the right term of this in by 28 and check out. And then we can go with the typical pyramid and the apex of it will be the final remainder. That is obvious, but what otherwise we can do is we can use Euler's theorem. And for that, you need to ensure that this divisor should be co-prime with each number. So if you are trying to divide 17 raised to 125 by 28, these two numbers should be co-prime. In this case, they are. And you need to find Euler's number of 28. So Euler's number here means you have to find out the numbers below 28 that are co-prime with 28, right? So for example, if I go by the brute force method, which all are the numbers co-prime with 28? 1 is obviously there, 2 is not there, 3 is co-prime with 28, the HCF is 1, 4 is not there, 5 is there, 6 and 28, the HCF is 2. 7, omit. 8, omit. 9 is welcome. 10, 11, 12, no. 13, yes. What am I doing? Trying to find out the numbers below 28 that are co-prime with 28, which means the HCF of 28 and that number is 1. I've come till 13. 14, it's not co-prime. 15, it is welcome. 16, it is not. 17, it is. 18, it is not. 19, it is. 20 is omitted. 21, no. 22, no. 23 is okay. 24, no. 25 is okay. 26, no. 27 is okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what this gentleman did is, this gentleman has reduced this work of ours. So what we simply need to do is, you multiply 28 by the way, the prime factors of 28 are 2 and 7 are the two prime factors. So multiply 28 by 1 minus 1 upon 2. Every second number is a multiple of 2, which means every other number is not a multiple of 2. Every seventh number is a multiple of 7. It means the rest are not multiples of 7. So this is 28 into half into 6 by 7. 14 2s are 28. 6 into 2 is 12. So this was just to prove that this works. You don't need to do this all the time. So the conventional or the brute force method that we used can be done simply by this, right? Okay. So if this is so, now coming back to the question, we have to find out the remainder first with the left term, and then we'll try and find out the remainder with the right term, and after that we'll simply add the two remainders to make the reduced form of it. So the first is, I have found out the Euler's number of 28 as 12. So what is the theory saying? Any number 7 raised to index that is a multiple of 12 will always leave a remainder 1, right? So if this is what you have, a number raised to en or any multiple of that, if this is the case, the remainder is always 1. So the Euler's number of 28 is 12. So 17 raised to any power that's a multiple of 12 is remainder 1. Unfortunately, 125 is not a multiple of 12. So let's make it that way. This is 17 into 120 into 17 raised to 5. So the Euler's number of 28 is 12. This is a multiple of 12. So this remainder is 1. And I just need to work out this. 17 raised to 5 is 17 into 17 into 17 into 17 into 17. 17 17s are 289. This is 289 and this is 17. 289 divided by 28, the remainder is 9. 28 tens are 280. So the remainder is 9. 9 and this is 17. 9 into 9 is 81. 81 divided by 28. 28 3s are 84. So this is 3 short of 84. The remainder is minus 3. So finally the remainder is minus 51. Redivide minus 51 by 28. The remainder is 28 2s are 56. Overshoot ho gaya. 28 1s are 28. Remainder is minus 23. And minus 23 remainder is same as plus 5. Minus 23 remainder is same as 28 minus 23. 5 is the remainder. First. Now I am working on this part. So that is 13 raised to 100 divided by 28. Again, I'll make this as a multiple of 28. 20, the Euler's number of 28 was 12. So I'll make a multiple of 12. So this is 96, simply because the shortest number, the closest number to 100, that's a multiple of 12 is 96. So this being multiple of 12, the remainder is 1. So I'm finding the remainder of this. So 13 raised to 4 is 13, 13, 13, 13. That's 169 and this is 169. 169 divided by 28. 28 6 are 120 and 48 168. 20 and 6 are 168. So remainder is 1. and here the remainder is 1. 13 was 4 times. 1 into 1 is finally 1. So the remainder here is 1, and the remainder in this case is 5. So my final answer is 5 plus 1, 6 is the remainder. Let me just check this out. Yep, it is 6 as the remainder. You can just have a look at this. I'll make it look proper. So this is how we reached the answer. 6 is the answer. You can take a screenshot of it. Slightly organized view. Consider the number n. What are we revising here? Number of all positive integral factors, number of all positive integral factor, and the sum of that. So the first identities for a given number, uh, the number of all positive integral factors is, you need to write that number as prime factors. 60, 30, 15. 15 is 3 into 5. So once you break it in string of prime numbers, simply add 1 to the index, add 1 to the next index, add 1 to the next index, and this is 4 into 2, 8, 8 into 2, 16 are the number of factors of this. So the number of factors are 16, 120. A quick check, number of factors of 120, 1, 2, 3, 4, 5, 6, 8, 10, 12, 15, 16 is not there, 18 is not there, 20, 24, 24 5s are, so 34s are, 43s are, 62s are, and 121s are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 is the total number of factors, right? So that's one. Don't do this. This was just to check or convince you. This is much reliable, simpler, faster, and equally accurate. Second, sum of all the positive factors. For you to find out sum of positive factors, again, this is the start. Break this up in 2 raised to 0, 1 is a factor, 2 raised to 1, 2 raised to 2, and stop at 2 raised to 3. This is highest. How about 3? It is 3 raised to 0, 1 is again a factor, 3 raised to 1, you'll have to stop at 1 because it's 3 raised to 1, the maximum. And in case of 5, it is 5 raised to 0 plus 5 raised to 1. So 1 plus 2 plus 4 plus 8 multiplied by 1 plus 3 multiplied by 1 plus 5. 8 into 10, 15 into 4 into 60 into 6 is 360. So sum of all these factors, if you add all them up, the addition is going to be 360. And that's what is this. So this is sum of all the factors. What is the sum of all the positive factors? If it is positive factors being asked, don't consider this. Only consider this. Which means I'll conveniently ignore this for odd factors. Which means this gets skipped up. This gets skipped up. And 4 into 6 is 24. 24 is the sum of all the odd factors. And I can very well check. This is odd number 1 and 3, 4 and 5, 9, 15 and 9, 24, and that's 24, right? How many odd factors are there? Again, omit this, 2 into 2, 4 odd factors are there. What is the sum of odd factors? Omit the even part. There's only one even prime number, and that is 2. So only the first part is to be omitted. Sum of all positive integral odd factors, sum of all factors is 360, odd is 360. What is the sum of all the even factors? We don't need maths here. Total is 360 and odd is 24. So 360 minus 24, that is 336, should be for even, right? But in case you want to know the maths behind it, so what you have to do is you have to follow this. It is just that this number 2 raised to 0, because it turns out to be odd. Anything raised to 0 is odd. You have to omit that. So in the case of even, you have to omit 2 raised to 0. So 2 raised to 1, 2 raised to 2, 2 raised to 3, 3 raised to 0, 3 raised to 1, 5 raised to 0, and 5 raised to 1. So this is 14 into 4 into 6. 240 and 96, 340 minus 4, 336. Right? No need to do that, but as I told you, the objective is to get this tool known to us. We never know how it will be used. It can be used in logical reasoning question or some other application of maths. So it's good to be a part of memory. So you can have a organized view of this. These are our answers. Find the sum of 25 natural numbers, 25 odd natural numbers, 25 even natural numbers. So again, there are set of identities for this. Sum of n natural numbers is n into n plus 1 divided by 2. Sum of n natural odd numbers is n square. Sum of first 25 natural even numbers is n into n plus 1, the generalized formula. Sum of the first n perfect squares is n into n plus 1 into 2n plus 1 divided by 6. And for perfect cubes, it is n into n plus 1 divided by 2, the square of that. That's it. So you just need to know this and use it wherever possible. So sum of the first 25 natural numbers is 25 into 26 divided by 2. 250 and 75 is 325. Sum of first 25 natural odd numbers is n square, that's 625. Sum of first 25 natural even numbers, 2, 4, 6, so on till 50, that will be 25 into 25 plus 1. So that's 25 into 26. 500 and 150 is 650, right? And sum of first 25 perfect squares. So this will be n into n plus 1 into 2n plus 1. That's 2 into 25, 50 plus 1 is 51 divided by 6. 3 2s are 6, 3 17s are 2 13s are. So that's 25 into 13 into 17 is 221. 4 5s are 20, 21, 4 5s are 21, 2 5. I'm just checking it. 25 ones are 25, 2 carry 50, 52, 5 carry 25 to the 55. So initially I simply divided it by 4 and then shifted the decimal 2 places. So 5525, and sum of the first 25 natural perfect cubes, it is the last one, that is n into n plus 1 divided by 2. We've already done that. We have to take the square of that, and how much is that? 325. So square of 25, 325 is 5 into 5 is 25, and 32 into 33. 33 2s are 66, 66, 72, 72625. So these are the identities you really need to be well versed with, and God knows where it will get. Quite a few times it gets used in geometric arithmetic progressions. Quite a few times, as I told you, in some intricate questions of LR and DI, and we simply end up using it. Just to check this. Oh, 325 square, I guess it was wrong. So I'm just checking it. 5 5s are 25. 32 into 33. 33 twos are 66. 33 threes are 99. I'm sorry, I made a mistake here. Here it is 105625. Otherwise, I think it was right. Right? What is the next identity? That was it. So there we are with the identities that are predominantly used in the number system, but they are not just having applications in number system, they are simply tools to be used almost everywhere except VARC. Almost everywhere it can be used. So it's good to know those things, right? See you all in the next session. Till then, goodbye.